Today we're going to talk about electron configurations. And in order to do that, and in order to set the stage for that, we have to review some concepts surrounding waves and wave function. And these are things that you have seen before in basic science, but you may have forgotten some of these things. So I want to go over briefly some of the concepts before we get into the more relevant material about electron configuration. First of all, you'll recall that a wave is a periodic motion that transfers energy. Periodic motion meaning that it fluctuates, it has peaks and troughs, and these several waves shown here. And the important part is that in the process of doing what it is doing, there is a transfer of energy through space. The wavelength is the distance from one peak or one trough to the next peak or the next trough. And you can see, for example, on the left here, lambda 1 represents one wavelength, lambda 2 represents another wavelength, lambda 3 represents a third wavelength, each of these becoming more and more rapid or more oscillating. The frequency is the number of cycles in a given period of time. For example, how many times a wave goes through a complete cycle in a second or a minute or an hour, etc. For example, again, you look at the left side, you'll see that each of the dotted lines, the distance between the two dotted lines represents 1 second. And so the first wave, lambda 1, the frequency is 4 cycles per second, or 4 hertz. In the second one, it's twice as quick, or 8 cycles per second. And then in the third one, lambda 3, frequency 3, it's 16 cycles per second, or 16 hertz. The amplitude is the height of the peak or the depth of the trough from the baseline. So you can have what's known as high amplitude waves. You see on the right here, there's A represents a higher amplitude. You notice that it's a measurement from the baseline to the peak. Or you can have a lower amplitude wave. And both of those waves have the same wavelength and also have the same frequency. Now, there's essentially two types of waves. There are mechanical waves, which have to travel through a medium, like water or air, etc. And then there are what are known as electromagnetic waves. And electromagnetic waves are waves that can travel through a vacuum, that do not require a medium. And this slide shows the various types of electromagnetic radiation. And they've been listed here in order of decreasing frequency, which means increasing wavelength. So on the left will be the highest frequency and smallest wavelength, and on the right will be the lowest frequency and the greatest wavelength. And because the energy is related to the frequency, the energy is going to be the highest on the left and the lowest on the right. So you can see in the middle here, approximately a little bit left of the middle, you see visible light, which is actually a very narrow band in the entire electromagnetic spectrum. Now the velocity of a wave, capital V, equals the frequency times the wavelength, and the wavelength is represented by lambda. Frequency is then expressed, and this is an attempt, it's a little v here, it's an attempt at actually a small case nu, I believe, what you can see here, the frequency is related to the velocity by the wavelength. And what this does is shows that if in electromagnetic radiation, the velocity is always the speed of light, which is represented by c. And so the velocity divided by the wavelength will give you the frequency. So these are a couple of formulas that you should keep in mind. But little v, you can also use the letter F to keep from getting confused, is equal to the speed of light divided by the wavelength. Now, the more important aspect of this is the aspect of energy. And what we want to show here is something known as the photoelectric effect. And the photoelectric effect occurs when a photon is ejected after a wave of a certain energy strikes a surface. So a stream of light particles that escape from a metal surface that occurs is related to the frequency of the wave that strikes the surface of the metal. You see that the frequency on the left here is higher, but does not have enough energy to cause the loss of a photon. But the other two, 550 and 400 frequency, both of these result in the ejection of photons. And you'll notice the speed is greater the lower the frequency, and that's because the energy is inversely related to the frequency. So the lower the frequency, the greater the energy, and the greater the ejection that occurs. And this formula, where the energy is equal to the Planck's constant, or h, times the frequency, or it's equal to Planck's constant times the speed of light divided by the wavelength. Now, this diagram shows you something known as a line spectrum. And these are the various lines you see at the top. Number 1 represents the broad spectrum of visible light, and it's a continuous spectrum. But if you shine if you apply a certain amount of energy to various substances, Na is sodium, H is hydrogen, Ca is calcium, and Hg is mercury, the photons that are released with the application of this energy are different, and they represent a very specific amount of energy, which is represented by the wavelength of light that is emitted, the strength of the photons that are emitted. So a line spectrum is a very narrow spectrum of light that has a very specific energy known as a quantum of energy. And if you compare this, the continuous spectrum, which is across the top, is a very broad amount of energy, and it sweeps a spectrum of energy, whereas the line spectra from various excited atoms comes from a very specific amount of energy. And what we will show in a couple of slides here is the fact that this specific energy, it results from changes in energy level caused by electrons moving from one orbit to another orbit. So here's the Bohr model of electrons, and how electrons, when they move from one energy level to another, they result in a certain quantum of energy. Because that energy is very specific, it results in a emission of light that is of a specific amount of energy, and therefore it's a line as opposed to a continuous spectrum. So the energies of electrons in an atom are quantized, and what that means is they have a very specific amount. It's like the steps on a ladder or the steps up into a house. You can get into a house two ways. You can either go up the steps, in which each change in elevation is quantized by the level of each step, versus you can go into the house, say, by a wheelchair ramp. That is, instead of being quantized, that's continuous, and the change of elevation is continuous. And what this shows is that electrons have a very specific amount of energy, and this is described in the quantum numbers. And these quantum numbers are unique for any specific electron. And we're going to talk at length about the quantum numbers related to electrons. An electron's energy increases when the distance of that electron increases from the nucleus. So the farther an electron is from the nucleus, the higher energy that electron. The discrete energy or lines that are result in the spectrum of elements results from this quantized amount of energy. Let me see if I can draw a diagram that will show this to some degree. What you have is, say this is the nucleus, and you have an electron that is flying around here. And from the outside, you apply some energy. And what happens is this electron will shift out to a higher energy level because of the application of the energy. Once this energy is removed, then the electron falls back into its normal state or ground state. In the process of doing that, it ejects this additional energy it had absorbed. And because when it does that, it causes a line spectrum. And this energy that results, it comes in the form of light. But the light is not a continuous spectrum, it's a line spectrum because it has a very specific amount of energy in it. And so that's what's meant when we talk about this. Now, when electrons are traveling in their orbit, they don't travel in a discrete circle. They actually have a wavelength. They travel as a wave phenomenon. And what this shows is that when an electron is viewed as it's traveling through its orbit and circling the nucleus, the wavelength that occurs has to have a whole number or an integer number of wavelengths in order for the circle to be completed appropriately. So, for example, here the wavelength can't have some decimal like 6.7 or something like that. It has to be a whole number or an integer number for this to fit, and this is called a standing wave model. And so the wavelength of an electron is going to equal Planck's constant divided by the momentum of that electron times its frequency. Now, there's an extremely important principle that governs the electrons, and it is called the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle is extremely important in quantum mechanics. And what it says is that it is impossible to determine simultaneously the momentum and position of an electron at any one time. Another way to think about the Heisenberg uncertainty principle is that when you measure some aspect, such as the velocity or position of an electron, you also alter its velocity and position. So it's impossible to make those kind of measurements without altering them, and that causes a degree of uncertainty. Now, the first number in the quantum theory is the primary number, what's called n, and n represents the energy level of the electron. So the principal quantum number, or n, represents the energy level of the electron, and it goes from 1 to 7. The highest principal quantum number is 7. And as you move out from the nucleus, the principal quantum number goes up, and the energy level of the electron that's associated with that principal quantum number goes up. These represent something called shells of electrons, and these are concentric circles of electrons, or electron paths, if you will, that radiate out from the nucleus that represent the area where you may find particular electrons with particular energy levels. I'm going to stop at this point, and you'll need to go to the next part of the lecture for a continued discussion on the quantum numbers.